Okay, so for our last video here, we're just going to take a look at another function here, and we're going to take a look at some analysis of like range values and domain values for certain other things. I just kind of wanted to note just one thing about some of the the textbook that we are using right now and that I'm pulling some of these examples from. They're kind of stingy with their notation in terms of if these graphs go on to infinity or not. So I just kind of wanted to address that in this video as well. If you do see a graph that extends all the way to the end like this, they are implying that there is a arrowhead on both of them. I'm just going to add them in manually so that we are kind of comfortable with that. But if you do see a graph that gets extended all the way to the edges, it is implying that there's an arrowhead and it extends to infinity from that. Just an FYI for you guys. Anyways, we have our x-axis over here. Looks like the scale is going up by 1 each box. And we have our y-axis. That scale is going up 2 each box. It's completely okay to have 2 different scales for x and y as long as they're consistent with themselves, basically. And we have our function f of x is equal to negative 3x plus 7. I'm just going to write that down for ourselves since we're going to be using that. Okay, so here we have the graph. Determine the range value when the domain is negative 2. Now remember, when we're talking about domain and range, this entire thing, f at x, which is our y coordinate, it's another way of saying y, this is actually our range. Another way to say that is this is our dependent variable, f at x. The thing that's inside of range here is actually going to be our domain. So x is going to be our domain, our independent variable or our horizontal axis over here. So determine the range value when the domain value is negative 2. So algebraically, we can just say that f at negative 2 equals negative 3 multiplied by negative 2 plus 7. Do a little math here, and we're going to get that this is equal to 13. And this is algebraically. Let's take a look on our graph though. When the domain value is negative 2, this is like saying x equals negative 2, just like we did algebraically. So when x is equal to negative 2, that's right here, let's follow this up to our function, right? Let's follow this up to our f at x line. And we're going to get that it's at this value, which if we read it off the vertical axis, looks like it's at 13. So algebraically and graphically also works. This is our range value now. So that's kind of like A over there. We can do B in a very similar way. Determine the domain value when the range value is 4. So if we set f at x, that's our range value, that's our y coordinates, that's all of these dependent coordinates here, a lot of different ways to say it, is equal to 4. We can follow the equation of the line, negative 3x plus 7, and set these two things to be equal to each other since they're both f at x. Negative 3x plus 7. Use our grade 9 techniques, minus 7, negative 3 equals negative 3x, and we're going to get 1 is equal to x. Let's go to the graph and let's see if that corresponds to what we know. So on the graph, if we go to a range value of 4, and remember range value 4, that's just like saying that y is equal to 4, or really f at x is equal to 4, either one will do. Well, here's our value. Let's go over to the line f of x, and now let's read it down to where x is. Oh hey, check it out, that's 1. So we know that this is right as well. So kind of a cool way that we can read graph, both algebraically, of course, if we have the equation, but also from the graph itself. As an aside, we should do one more question, and this would be looking at what is the domain and range of this graph. Domain and range of this graph, but also of this equation as well. Now, if we wanted to do it in terms of set notation, this is pretty cool. All we would have to do is this. It's the real numbers. It extends to infinity this way, and that would be to negative infinity for our x values. Extends to positive infinity for x values in this direction as well. So we would just say real numbers, negative infinity, positive infinity. If we wanted to, we could do this in interval notation and say it's negative infinity to positive infinity like that. Our range would be literally the same thing. It would extend from negative infinity all the way down there to positive infinity, which would be, I can do better than that, which would be the real number system. So that would be, in set notation, what the range would be for this function. Also, if we wanted to do it in interval, negative infinity to positive infinity. Kind of cool stuff. Neat little extension there. And that should cap it off for this lesson.